Okay, so let's start ours today. So, uh, sorry, last time I spent too much on the uh Legendre stuff. So let's focus on the uh um periodicity argument. Okay, so uh. So okay, so this okay. So so okay, so let's do a change of variable here, right? So so let's do a so what do I want? So I want to have this C1 to be so for the C1, right? So basically what I want to do is that I want to make like a minus sign, right? I want to shift the or yeah, for the C3T, what I want is that I want to maybe shift the direction of this C3T, right? So okay, so if we shift the direction of the C3T, then I think we will just get the negative sign, right? So what we showed last time. So yeah, so it will be like a minus, right? If we shift the direction of this C3T. So basically, so basically this C3T is like going around like that. If we shift the direction of this C3T. So now this omega 1 just becomes this T, right? So it becomes A plus T times omega 1. Right. So when T equal to 0, yes, okay. So, and then when we evaluate this one, so what do we get? When we take the derivative, what we have is that we have the derivative as just the omega 1, right? Yeah, so sorry, this might be a little bit ambiguous here. So 1 plus, so A plus, this is T times omega 1. Okay, so, and then the parameterization inside. So 1 plus omega 2 plus T times omega 1. Okay, so Okay, so let's do a change of variable. So, okay, so I think the change of variable will still work for the complex line integral, but I was not sure exactly from this definition, right? So basically, I need to break it. Basically, we need to break it down into like some inner part and imaginary part, and then do the change of variable. But yeah, so maybe I'll leave it as an exercise to show the change of variable works here. So yeah, but I will just say that. So let's say like the exercise. Namely, basically, I think what's really going on is that we let this zeta of we let zeta so basically let zeta z to be equal to uz plus ivz, right? And then we do the change of variable, and then we separate this omega 1 as the real part and the imaginary parts, like let's say x1 plus y1, right? And then compute the corresponding to the, and then do the like real part and imaginary part separately in the computation here, right? And then we do the change of, then compute. Okay, yeah, so let me do this. So then we do the change of variables. We do the change of variables. As so we integrate from 0 to 1 of this u. So basically we plug in u of this a plus w2 plus t omega 1 plus iv of the same thing, right? So a plus omega 2 plus I omega 1, and then whole thing times omega 1, which is xi plus I yy, and then dt. Okay. Yeah. So I think the change of variables, if we just do it in this way, and then when we just separate it, and then separate into the real part and imaginary part using this formula, eventually I think they will be the same. But I'll leave it as an exercise. Maybe later on I can check. Okay. But now let's just move on with by just doing the change of variable here. Okay. So what is our what is the change of variable that's gonna be? So here we let and see if it agrees. Okay, and see and check that it agrees with the that it agrees with the with the complex case. Okay. Okay. Yeah. So we will check that later. Okay, we will check that later. Okay. Maybe as an exercise video. Okay. All right. So let's say the like a change of variables for this formula. So let's say that so this is the formula. Let's say equation 1. Okay, and maybe later on we'll do this again for this one. Okay. So so for equation 1, what we have is that S to be omega 2 plus t omega 1. Okay. Omega 2 plus t omega 1. And then we have, let's see, so we have ds is equal to omega 1 dt, right? Okay. And then, so what happened is that, so then, okay, then 1 becomes let's see, so when t equal to 0, okay, so t equal to 0, s is equal to omega 2, and then when t equal to 1, s is equal to omega 2 plus omega 1, right? Okay. Okay, so then 1 becomes hold on. Okay, so let's see. So wait, hold on 1 second. So what is the change of s is equal to, wait, I don't think we can, I don't think I can really do that. Yeah. Because I cannot really let no. I don't think I can do that. Because this t basically is the index variable that runs from. Oh, I see. That's why we have that, right? We don't do the change of variable from here, right? But we do a change of variable using this periodicity argument, right? Yeah. Okay. So. Okay. Yeah. So we don't do the change of variable using like just s and t, because if we use s, right? So this I don't think they kind of correspond to the same type of variable, because if we let s to be like yeah, so it is really like a linear transformation, right? So this is like we going like down below, and then here we are going down above. Yeah, so And also this t is like a one-dimensional thing, right? So I can't make it have a vector or direction or something. It's not possible, I think. Yeah, anyway, so I think we need to apply this relation, right? So basically, after, so this is the down below, and then after we add like omega 2, that's correspond to the same thing as the same, but yeah, when we like add omega 2, is the same thing as we add eta 2, okay. Okay, so this is the thing that we need right now, okay. So, okay, so we can delete this one, okay. Okay, so now, using the periodicity relation, okay, so using the periodicity of zeta z, we now have that this 1, okay, so we don't need to care about the exercise anymore, okay. So 1 is equal to let's see. So I think instead of doing 1, right? Because this 1 is already added. It's yeah. So maybe let's just do this one. Okay, instead of doing 1. So let's maybe do this one. So okay, so I'll just call this one as 1. Okay. So call this one as 1, and then maybe yeah, so call this as 1. And okay, so so 1 becomes the integral from, wait, I was wrong. Yeah, because I need to use this one because so this is the thing. This is the original stuff. This is the original stuff, and this one is the original stuff plus omega 2, right? So yeah. So therefore I need to change this one to the original stuff, which is the one here, plus the eta 2. Okay. Yeah. So here I want this one to be just a 1. Okay, so and then 1 becomes, okay, so now we can do the change. So for integral from 0 to 1, zeta of the original stuff, a plus t omega 1, right? And then the omega 2 comes as plus eta 2, okay. And then whole thing times omega 1. Okay. dt. Okay. Okay. So now what we have is that okay, so now yeah, so maybe let's call this A, okay. So now we just combine these two terms together, okay. So now this A, this at, okay, A is a circle, is at minus 1, okay, becomes is equal to so here I have this one times this guy times omega 1, right? So this guy times omega 1. This is being cancelled out, okay. So what is left is just the integral from 0 to 1. Because here there's a negative sign, right? So there's a negative sign. So here this is negative eta 2 times omega 1 dt. Okay, so which is just equal to negative eta 2 times omega 1. Okay, and then same thing here, right? So so what do we do? So first we apply a let's see. So what do we want? So let's first apply an argument here, right? So basically this C4, I change the direction of the C4 and then I add a negative sign, right? Okay. So I change the direction and then I add a negative sign. So then this becomes yeah. So now this C4 becomes this A plus T. So sorry, C4 tilde, right? Becomes A plus T omega 2. Okay. So that the derivative is just omega 2, right? Derivative at T, which is equal to just omega 2. Okay. So now, so this becomes okay, so now this becomes just the A plus omega 2. Sorry, A plus T omega 2, okay. And then times that, and then there's a minus sign, okay. Alright, so now we apply the same argument, but to this guy, right? So let's call this one 2, and then let's call this B, okay. So now, so using the same argument, but maybe you use this one, okay. So using the same argument. So we have so okay, so I want more to write it down. So because this 2 becomes just this so this is equal to so this is equal to this zeta of A plus T omega 2, right? Plus, so this is eta 1, okay, so this should be, yeah, so it should be eta 1, okay, and then whole thing times omega 2, right? Okay, so this whole thing times omega 2, and then minus this guy, right, times omega 2, okay, so what's left is just the so we have this eta 1 times omega 2, right? So 2 minus, let's say B, okay, is equal to the positive integral from 0 to 1 of eta 1 omega 2, okay, so which is just equal to, sorry, there should be a dt, okay, dt, okay, so which is equal to just eta 1 omega 2. All right, so we don't need the exercise anymore. Okay. All right, so okay, so now, then the whole thing just implies that, so now we have the integral over the boundary of the parallelogram, right? Dz, so this is equal to okay, so yeah, so this is equal to okay, so eta 1 omega 2 minus eta 2 omega 1. Okay. Oh, okay, yeah. And then by the previous argument, right? So in the previous argument, we show that by the Cauchy residue theorem, yeah. So this is equal to and also the one number argument, right? So we show that this guy is and we know that this guy is also equal to like 2 pi I, right? So this is equal to 2 pi I, okay. 2 pi I. Okay. Okay, so this is the Legendre relation. Okay. Okay. All right. So okay, so let's see. So okay, so let's go on. Okay, so now let's see. So let's continue. Okay, so the integration. Can be carried one step further. One step further. Provided that we use an exponential to eliminate the multiple valueness. To eliminate the multivalueness, the multiple valueness. Okay, so just as easily we okay, so we can verify directly that the product sigma z, which is equal to z times the product of omega not equal to 0. of 1 minus z over omega e to the z over omega plus 1/2 z over omega squared. Z over omega squared. Okay, so he is calling. So let's call this equation 13. Okay. The product converges. Okay. And represents an entire function can verify directly that the product converges and presents an entire function which satisfies. Okay. Yeah, so we will see why it verified directly. Okay, so which satisfies okay, so sigma prime z over sigma z is equal to zeta z. Okay. Okay. So yeah, so let's first check that this product converges. Okay. So check. Sigma z converges. Do we use the Weierstrass M test? Or what test do we use? Yeah. Okay, so let's use the Weierstrass M test to see whether this one is converging or not. So let's say using M test. Yeah, is it a version of convergent test? Because this one is like an infinite product, right? But M test, yeah. So let me see. So oh, okay. I think there is a test for infinite product. Yeah, I think there's a test for infinite product. Yeah, because okay, so let's try check it like wait. Okay, let's try M test first. Okay, let's try M test first. So, so first, okay. So our first step basically is yeah. So so let's fix a compact set K. Okay. And then, so in order to use M test, so we need to show that. Yeah. So yeah. So yeah, M test is about series. Yeah. So this is not a series, right? So this is just an even product. But it can become the series when we apply the product. It becomes a series of the exponentials, right? But there are still some problems about the product terms that at front, right? So, so let's see. So, this one. So first we fix the enumeration. Okay. So we need to show that it converges absolutely, right? We need to show the absolute uniform convergence first in order to show that this is a well-defined product. So be an enumeration of this of the lattice point. Okay. So in the past I used the notation wedge to denote the lattice point. Okay. Maybe like I have to exclude 0 or something, but yeah, I use wedge to denote all the lattice point that is not 0. Okay. And then so maybe yeah, I use this notation to denote the lattice point, excluding 0. Okay. So so now so let's define let's define the partial product, okay, to be defined as z times the product of I from 1 to n of okay, 1 minus z over omega I times e to the z over omega I plus 1/2 times z over omega I squared, right? Okay. So this is equal to what? So this is equal to, so here it has two parts, right? So one part is the part that corresponds to the infinite product. So here, yeah, so this corresponds to the infinite product. Not infinite product, but the finite product. And then times, so maybe I use the bracket to denote that this product only applies to this guy. And then, so this guy becomes the sum on the exponentials, right? So z over omega I plus 1/2 times z over omega I squared so I think we can, what we can do is that we can verify that this guy and this guy converges because we are aiming to show that this guy is converging, this sequence of functions is converging locally uniformly on this compact set, right? So if we can show that so basically, so it consists of like these two parts, right? So if we can show that these two parts converges separately, right? If I can show that these two parts, so our strategy, right? So that so current strategy, okay, so that fn to be equal to let's say fnz, okay, to be equal to the finite product I from 1 to n of this guy, and then that gnz to be equal to the e to the partial sums, right? Z over omega I plus 1/2 times Z over omega I squared. So and then if we show that this f and z converges uniformly on this compact size k, and then we also show that this g and z also converges uniformly on this compact size k. So maybe this theta and z, maybe not uniformly but absolutely, I think. Yeah, absolutely. Yeah, so maybe it can give us some some insights on this one. Okay, so yeah, so yeah, I'm running out of time tonight. So yeah, so I will try to continue next time. Okay. So try to show f n z g n z converges uniformly on k. Okay. All right.